Hello everybody, my name is Leo, and today I'll talk to you a little bit about a project that I've been working on, which is to get quadrupedal robots to climb hills. In front of you are basically the three main things that I've done. I've trained a robot in a simulator called Isaac Sim, and I then validated the policy of that robot on another simulator called Majoko, and then deployed that policy in the real world on an actual robot. I'll then tell you a little bit about sort of the process it took to get to these three stages. So we'll start with the motivating premise of this project, and then I'll talk about a big part of this project, which is the reward tuning to get these behaviors out of these robots using reinforcement learning. And then I'll tell you a little bit about the transferring process of getting a policy that works in simulation to work in the real world. Okay, so why do I find hill climbing robots to be interesting? Well, the reason why is because I see mountain goats as a proof of concept of what this project could be. You know, I think it's really stunning to see these mountain goats climbing dams and just like jumping across rocks on cliffs without any effort. I find that really inspiring, and I wonder if we can get a quadrupedal robot to do the same thing. I think it would be just really cool to look at, and I think there will also be a lot of meaningful applications for such an invention. In the literature, there are basically two main ways to get robots to climb steep hills. The first one is model-based. These people worked on a policy that makes sure that the body's center of gravity is always within a support plane. This leads to basically a very slow gait, certainly not as fast as a mountain goat, but it's very stable and it can climb pretty steep hills, up to 60 degrees. And then the second one is deep reinforcement learning. And I have not seen a deep reinforcement learning policy specifically for cliff climbing, but there have been general purpose ones that can climb pretty steeply. What you see here is a deep RL policy trained to climb 45-degree slopes. In my project, I'm asking the question, like, are there any specific environmental designs or reward designs that could push a policy to learn the climbing of steep hills specifically? Yep, so those are my research questions of what modifications in the task design is required for cliff climbing, and by doing it, I hope to get to some sort of synthesis of what the limits of a deep RL controller are. This is the general setup of my experiment. We're using reinforcement learning, so this is in a Markov decision process. We're using proximal policy optimization to tune the network. The action will be joint positions, and then the simulation is going to be using Isaac Sim with Isaac Lab as the reinforcement learning framework that's built on top of it. And the observations, we're just going to start with the joint state, the orientation, so like the yaw, pitch, and roll, and also the last action of the robot, as well as, of course, a velocity command to tell the robot where it should go. And to motivate the RL policy, I'm going to give it basically velocity tracking rewards, and then we're going to be penalizing joint acceleration, joint torque, and action rate to make sure the robot doesn't expend that much energy. So how did this initial reward and observation mix play out? Well, not well. As you can see, it converged to something that's not exactly climbing. And then I find out that the reason why it behaved like this is because I was accidentally spotting robots in midair. So at the very beginning, it was dropping onto the ground, which is not great. But after fixing spawning, I'm still getting this behavior. So what might be able to fix it? And I first thought, okay, well, why don't we take a flat walking behavior, a policy, and then put the policy in a hilly environment that would basically build on top of those weights. And as we can see, it does work. It does work. The robot can climb some shallower hills. And so now I basically thought, okay, it's great it can climb shallower hills, but why couldn't it climb the steeper ones? And I thought maybe I should make this environment easier by giving it some ridges first. But it seems like it was still too hard for the robot. And so I started to look at the reward graphs and found that the robot is taking the joint acceleration penalties very seriously. And that's basically devaluing the most important reward that I should be optimizing for, which is the command tracking reward. So I decided that we need to make sure that there's maximum signal in this thing. And so we need to maximize the command tracking reward. So I removed every other reward except for that. And the robot now started to do much better. It started to climb the ridges, but still not well. So I looked at sort of the information in the training and found that, the robot has a steady improvement, and then it maybe forgot about what it has learned, and so the performance has degraded. I looked at another policy to see if maybe my hyperparameters were off, but that ended up not being the case, as other policies with the same hyperparameters performed pretty well. So I looked at the observations and saw that I was only giving it joint space observations. So it was only looking at the joint angles and the joint velocities of the robot, which is really hard for a robot to be able to act on, because it has to somehow infer its task space velocities based on those joint states, which is a pretty hard computational problem. So I just added its space reference to the observation, and that ended up improving the performance of this policy. Okay, but now there's another problem. So it's performing much better now. It's going to 4.5, but it still forgets what it's learned, even though the reward doesn't seem to change. So I looked at, that's not good. Okay, so then I looked at the rollout and noticed that the green, which shows the commanded heading, doesn't actually point to the top of the hill, right? It always points to whatever that's in front of the robot. I'm just spawning the robot to be pointing towards the hill, hoping that the robot doesn't deviate from its front direction. But of course it does, because the hill would basically push it sideways. And so what I changed was to make a command manager that basically always points to the top of the hill. And that gave us pretty good behavior. So now the robot can climb to the top of the hill. And here's the final reward. Basically, yeah, it's mainly the tracking rewards, and I found that it's helpful to penalize thigh contact and body contact, because I was noticing that the robot was scuttling a lot, and that of course is really not good on a physical robot. And for the final observations, as we've talked about, I just added some task space observations, which made the policy learn much easier. So going back to the two research questions, I think the main lessons of this experiment is that when you're thinking about getting a specialized policy, you need to think really hard on how we can make better command managers. Because for a flat walk policy, which is a lot of reinforcement learning policies for locomotion, you just have to sample from a distribution of velocity vectors, and you're good, right? But if you want a robot to climb up a hill, you need to have a way of getting the command manager to always make sure the robot is rewarded for going up the hill instead of choosing an easier, instead of like hacking the reward, right? So that's a very important consideration that I think people might ignore at first. And it's also a pretty complicated one to think about, because if you're only rewarding the robot to go towards the top of the hill, it's not learning any other behavior, right? Like, I was rewarding the robot to always make sure that its front is pointing towards the top of the hill, but that will mean that it's not learning how to basically side climb, so strafe towards the top of the hill. And that could be an issue in the real world, because you sort of need that robustness. So this is something that's actually pretty hard to do. And secondly, it's important to add base references. It reduces sort of like the learning load of the neural network. And then a general practice for reward tuning is just to always start with the signal and then add your fine tuning. And the second research question is still unanswered. I don't think I've done nearly enough to truly understand the limits of deep reinforcement learning. Okay, so we have a workable policy. Let's think about how to get it in the real world. I first looked at Quad SDK, which is the quadrupedal sort of software suite that my lab has developed, the robomechanics lab has developed. But I ran into a lot of software issues. The learned policy package was still in development, and there were a lot of bugs. So I ended up switching to Unitree's official sort of deployment software. And when you're doing deployment, it's really important to first start with a sim to sim transfer to make sure that the policy is not overfitting to the specific nuances of the simulator it was trained on. So I had this robot run in Majoko. It seemed to run okay. And because I was still learning a lot about how to get a policy deployed, I used another policy, not my own, for simplicity's sake, to make sure that wasn't anything wrong with my policy that was causing the issues. And then after sim to sim transfer, we can do sim to real. And as you can see, it walks pretty nicely. It was surprisingly fast. Okay, so here are the takeaways of this project. This was my first exposure to deep learning in general, as well as reinforcement learning, as well as how to work with quadrupedal robots, ROS2. All of this was really new to me. I was a freshman undergrad when I took on this project, so I learned a lot from this. And I think an underemphasized topic that takes a lot of time to learn is just like to install software and how to manage dependencies. It took me a lot of time to install Unitree SDK, Quad SDK, as well as its Onyx runtime package, which is a package you need to run inference. I had to learn a lot about like dynamic linking and some computer systems concepts. And there's also a lot of small things that one needs to know in order to train policies on high performance compute clusters. I learned a lot about writing batch scripts. So for the next step of this project, I think it's important for me to benchmark my environment versus the Isaac Lab example environment to see if indeed a specialized policy works better than a general policy. And then of course I want my policy to actually run in the real world to see how it performs. And then I think it would be very important to incorporate vision observation so the robot can actually see. And then we'll be able to start training policies that help the robot navigate. A North Star for this project is for me to slowly recreate bits and pieces of the Robot Systems Lab's Robot Parkour paper, which is my favorite robotics paper because it's like an end-to-end deep RL system that works really well. And yeah, I hope I can get there. I think it would be really interesting to think about the problems related to hierarchical policy structures where you have a deep learning, a navigational policy choosing different skills. And lastly, I just want to thank the people who helped me with this project. Professor Aaron Johnson, who's the PI of the Road Mechanics Lab, and my mentor, David Oligan. This project wouldn't have happened without their mentorship and support. Okay, thank you for listening to my talk, and I hope you learned something.